Huh? Oh, you don't understand the question. Okay. All right. So we have this compound, right? This is a crown ether. Phenanthrene is water soluble. Phenanthrene is soluble in organic solvents like hexane or benzene, like that. This compound is also soluble in hexane, benzene, all that stuff. Now, in order for phenanthrene to be able to emit, what do you need to do? What else you have to add to this solution to make it work, to see phosphorescence at room temperature? Question clear? Still not clear? Okay. Okay. You know, the one of the most important criterion is to enhance the rate of the spin orbital coupling, intersystem crossing, and then the radiative rate constant. So having phenanthrene here and this one next to it is not going to solve the problem. So one thing that you need to do is somehow or other you will have to bring in a heavier atom like rubidium or cesium, like that. Okay. So if you dissolve the salt, you will think, okay, I cannot put rubidium chloride in organic solvents, so it is not going to dissolve. That is not true, because what will happen? This is the invention of Pedersen, who got the Nobel Prize, to show that it is possible to dissolve inorganic material in organic solvents. So if you take rubidium chloride, rubidium will go here, and your phenanthrene is somewhere here. So the rubidium, once it goes inside, the chloride also will go in the water. So like a sodium chloride, the salt that you eat every day, it is soluble in water. You think it is not soluble in hexane, but you can dissolve sodium chloride in hexane provided you add a little bit of crown ether to the hexane. Okay. So now, so you take for example naphthalene, right? This is a normal naphthalene. This compound is not going to show phosphorescence, okay, because there is no way the rate constants are going to change. Suppose you are able to somehow bring in sodium chloride, or effectively you have to bring in something which is heavier like rubidium, cesium, or lead, that we had a table, and you bring it in. Now that rubidium that is sitting on top of it will enhance the intersystem crossing, and you will start seeing phosphorescence. Okay, here is a table. I don't have a figure for this. Okay, let me see here. Okay. See, this is the radiative rate constant. See the radiative rate constants. Okay, that is tells you the phosphorescence, how intense the phosphorescence is. If nothing else, nothing is there, it is 8.7. If you add a little bit of cesium chloride, it is 81. So it goes by 10 times, and the fluorescence comes down. Or the radiative, going intersystem crossing is also increasing. So basically, having a heavier atom, cesium chloride, but this is not in water, this is in organic solvents, and you can make this compound to show phosphorescence, because the cesium will complex here, and once it complexes, that is water soluble, and then this whole thing, you can see at room temperature. Okay, here is, okay. Now here is a picture. Tell me, this is the naphthalene. I have been saying naphthalene for a while. So naphthalene in micelles. Okay, so here is SDS, that is a sodium dodecyl sulfate. The soap that you are using every day, it is a long chain acid with some kind of a metal ion. So it can be sodium, or it can be rubidium or thallium or lead or whatever, if it is. So normally sodium, what do we use? Sodium dodecyl sulfate. Dodecyl means at least 12 carbons are there, 12 CH2s. Sulfate is a sulfate anion, and then there is a metal ion which is sodium plus. Okay. Now if you read the caption, micelles as host, naphthalene at SDS micelles, effect of heavy atom counter ions. Okay. So this is the normal emission of naphthalene in water in sodium dodecyl sulfate. Okay. This is the sodium, the micelle structure. Micelles looks like a small ball, and then the naphthalene, which is not water soluble, it will go inside here, because if you put it in water, it doesn't want to be here, it wants to go inside. Now the emission looks like this. But if you change this sodium into something else, as you see here, completely the fluorescence is gone. And now what you see is the phosphorescence. So you switch the fluorescence from phosphorescence in the same micelles, but changing something. What is that has been changed? That is the question for you. So whoever, this is somebody had a bright idea. Okay, I want to see phosphorescence from naphthalene at room temperature. In the textbook it says I cannot see. So now he figured out a way to see that. So take the micelles and you change the something on this SDS, and then you see it here. You can see there is 0 phosphorescence here, and this one there is only phosphorescence. The only difference is there is one micelle here, there is a different micelle here. So what is the difference between the two? What's the difference between the two? In fact, the answer is there on the slide. Okay. Okay, remember Monday morning 10 o'clock is a test. Monday, July 1st, 10 to 11, and then if you do it early, you have a break. So before that, you have to know all this stuff. And I will give you Saturday and Sunday. You can read the whole thing, and then you will be prepared. You will get 100%. Okay, what is the thing? What is the thing? See, for example, this is the same micelles here and here. In one case, you see only fluorescence. In the other case, you see only phosphorescence. So what was it done to see the phosphorescence?
Because the different heavy atom.
Okay. What is the heavy atom? What different? What's the difference?
The left one is sodium, but the right one is T.
Huh?
The left one is sodium.
Yeah, that is clear. And then the other one?
The other one is TI. I think the TI may be more heavy than the sodium.
Okay, you are correct. I think you are struggling to figure out what is TL. So TL, if you go to the periodic table, TL is thallium. Okay, the thallium is much heavier because if you remember we had a table. In the table, let's see over here. Here, thallium is 3,410, sodium is 11.5, and you see there's a huge difference between this and this. So when you change the here sodium chloride to thallium chloride, and then now you can see this is immediately showing up the phosphorescence, and the fluorescence went away. Here this micelles has got a sulfate group at the end, sulfonate. That is why sodium dodecyl sulfate. So there is a minus charge. The minus charge will attract the positive charge, which is sodium. In this case, the thallium. So this thallium is going to be somewhere here, all over the place. There is a lot of thallium, and your compound is sitting inside, and without knowing whether it is what is going to happen to that. So when the thallium is there, then you see only phosphorescence. Okay, so all you need to do is take the soap, exchange with the thallium, and then you will see this. Okay, so here. Now this is basically the same naphthalene in zeolites. Okay, here lithium zeolite. X means it is a zeolite. Lithium X, and then this one is rubidium cesium. Cesium is green, and then rubidium is red, and lithium is blue. You see here, when there is lithium as a cation, there is nothing here. The emission in this part is there are two emissions. There is one emission here and one emission here. Tell me which one is fluorescence, which one is phosphorescence. You are expert on fluorescence and phosphorescence. Which one is fluorescence, which is phosphorescence? What's that? Fluorescence. Okay. Okay. So if you look at the bottom of the axis here, so we said always the singlet will be at a higher energy than the triplet. So the 300, this region is 300 to 450, and this region is 450 to 700. This is a longer wavelength, means lesser energy. So this is fluorescent, that is phosphorescence. So the same naphthalene, depending upon what type of cation is inside the zeolite, it shows different emissions. So if you have lithium, it shows only fluorescence. If you have cesium, it has a little bit of fluorescence, but mostly phosphorescence. Okay, tell me why. Okay. So if we go back to the same table, lithium, and so see in the periodic table, sodium, potassium, and then rubidium, cesium, thallium, like that. It goes in the last periodic table. And if you go back to this table I showed you, let's see. So if you go back here, sodium, potassium, rubidium, and cesium, you can see this is 11, 38, 160, 370. So this number is slowly increasing. As the number is increasing, the phosphorescence keeps going up, because the higher the atomic number, faster the rate gets. The faster it is, the more intense the phosphorescence is. So you can see this thing. So suppose you want to have, for example, looking at the table here, if I want to see phosphorescence, very intense phosphorescence, which one of these things I would use? Would I use cesium or sodium or lead? Which one I would use to see the effect? Okay. If I want to see the emission from naphthalene at room temperature, phosphorescence, and then for example in the zeolite that we showed, okay, let's see here. The zeolite is basically this one. Okay. The zeolite is this. These circles here, they tell you the cations, where they are in the zeolite. It is known. If you put a sodium or something, they will go here, here, and all these three places, sodium will go and sit inside. So these circles represent the cation, and your organic compound is going to go here. If I want to see phosphorescence from this compound that is sitting here, will this be lithium, sodium, or thallium, or or lead? Which of these will give me a good phosphorescence, a strong phosphorescence? You don't want to see even a little bit of fluorescence. We want everything to be only phosphorescence. Which of these? So basically, what you can do, you can take the zeolite, and then you can crush it with the sodium chloride or cesium chloride, and then if you just grind it, the ion will go inside. Okay. So which one would you take? Will you take thallium, or will you take sodium, or you will take rubidium to get the strongest phosphorescence possible? Which one would you take? Thallium. Okay, so you know the answer. So if you say it earlier, then we can go for lunch earlier. Okay, so that is what you can see here. See, this is you can see there is a direct relationship between the atomic number and the intensity of the fluorescence. Very intense fluorescence with lithium, because it doesn't have a strong spin orbital coupling. Rubidium has got some, cesium has got even heavier than lithium. So in the case of cesium, everything is pushed towards the phosphorescence. Okay. So if you go back to the table here, for example, this is the atomic number square. You can see the rate constant for the phosphorescence is basically increases with the atomic number. Okay. And whether it is, the crown ether, or whether it is a zeolite, or whether it is something which is attached directly. So all compounds, this is aromatic compounds, for example, anthracene, phenanthrene, and then this is chrysene, pyrene. You can see phosphorescence from all of these compounds, but it has to be in the presence of heavy atoms. For example, all of these things are inside the zeolite with the thallium as the cation. The thallium as a cation, you can see that, but if you take it in a normal solution every day, you will not see the phosphorescence. Okay, that is because you need the heavy atom to enhance this stuff. Okay, here there are some olefins. Okay, the other thing is, the reason that you don't see phosphorescence from most compounds, it is because it undergoes quenching by oxygen. Oxygen, the triplet energy of oxygen is only 22 kilocalories. Every other compound is above 22. So oxygen, when it interacts with this compound, it will take the energy away from the compound, and then you will not have any triplets left. Okay. So if you really want to see phosphorescence, now you have to worry about removing the oxygen from the, or you should not allow oxygen to access your compound. Okay. So for example, the excited singlet, it goes to the triplet. Okay. So this rate constant, and then there is something else happens, and in the triplet state, we said triplet will have a long lifetime. A long lifetime means something else can come and take the energy away, and that would be normally oxygen, or it is something else. It can be anything, but it is oxygen is what happens. So if you don't want something else to access your compound, then you will have to protect your compound completely away from something else. So if you don't want somebody else to come inside the room, you just close the door. If you leave it open, somebody else will walk in. Okay, here there is an organic compound. When it is excited, it goes to the excited state, and in the excited state, if it meets itself, then it will undergo what is called as self-quenching. Some compounds, they do this stuff. So you take one compound, you take it to the excited state, and then leave it there, and then the same compound in the ground state, if they come and heat it, the energy will go. So you don't want the collision between excited molecule and the ground state molecule. This is called self-quenching. This happens for some compounds. So if you stop this process, then this molecule will have at least some chance of emitting phosphorescence. Otherwise, this molecule is going to come and then it will go away. So one way to stop this thing is, you take your molecule, put it inside a small container, and then produce the triplet, and as long as it is inside the container, the other molecule cannot come and hit it directly. Okay. So in everyday organic solvents, you cannot put the molecule in a container. So that's where and also if there is a molecule is in the container, it cannot react with oxygen. So this process is also bad news. So this undergoes quenching, this undergoes self-quenching, and both of these things are unfortunately making this compound not to emit phosphorescence. Okay. So we can stop this process. We can stop both of these things. The only thing is, you put it inside. Yes, like if you put the compound inside this bottle, and then other one cannot come and hit the compound. If it is left in the beaker, other compound can come and hit it. Okay. So let's see here what happens. This is something, this one is a compound. Put it inside a barrel like this. This is an cyclodextrins or cucurbutyryls. They all have, I showed you at the very beginning, the structures looks like a small barrel. Okay, this is a compound. Say for example, cyclodextrins. And if you put the molecule here, that molecule is surrounded by this big barrel. So another molecule cannot come and hit this. When it's hitting it, it will hit only the outside walls of the barrel. Inside compound is very safe. It is like a soldier sitting in a tank. The tank is now you take, for example, these are all the compounds. So this molecule is the one that is going to emit phosphorescence. Okay. You take only one example here. You take this compound, camphor thione. Camphor thione is this one. So this one, the blue line is in some solvent. The blue line is, I don't have this. Oh, this is here. This is in a perfluorodimethyl-cyclohexane. There is no emission. Okay. This molecule is soluble in the solvent, but no emission. But you take the same molecule inside the octaacid, that is this one, and this one is put it inside here, and then immediately there is a strong emission. Okay. That is because what happens is, if this molecule is excited in a solution, another molecule of the same one comes and then interacts with this. They just share the energy and then goes back to the ground state. But now, if it is sitting inside the barrel, another one comes and hit it, it is going to hit only this outside. It is not hitting the molecule that is inside. So inside molecule is well protected. You can see it just immediately goes up. In all these cases, the emission immediately goes up. Okay. You can see, same sort of stuff. You can use whatever you want. Basically, this molecule is, you put a small molecule and build around a small cage, and then the cage is the one which is protecting this molecule. These things are easy to get. For example, this is called cucurbitryls, and this is you can make it or you can buy it, and once you put it in water and shake, this compound will go inside. So because these compounds are not water soluble, these compounds, this is the one that is sitting inside. As long as it is in water, it will not dissolve. But if you add a little bit of this will dissolve. That means it goes inside the thing and then stay there. You can see, okay. So the thing is, although we study phosphorescence are hard to see, you can make molecules to show phosphorescence. But you have to know, to see phosphorescence, you have to do two things. You have to enhance the singlet triplet crossing, and you also have to stop all the quenching. The triplet has lives for a longer time. Something else can come and quench the triplet. You want to avoid both of them. You want to avoid the quenching, enhance the intersystem crossing. You can enhance the intersystem crossing by using heavy atom like various cesium, thallium, iodine, like that, and then you can stop the quenching by putting the molecule inside the barrel. Okay? Questions? No? Okay. All right. So we have more time. We'll see some more things. Okay, here. Do you remember this picture? This figure you remember from yesterday? Okay. So pyrene forms hexamer. And I told you, to form the hexamer, you have to increase the concentration to like 10 millimolar. Okay. So if you have this molecule, a tiny amount, there is about 0.01 millimolar, that is about 10 micromolar, you will not see the hexamer. Okay. So to see the hexamer, you have to have a pyrene, another pyrene, so they have to come and interact, and then you will see the emission. But then, if you take like micromolar concentration, you will not see any hexamer. But somehow, if you can bring them closer, whether it is micromolar or it is even dilute concentration, you will see a very strong hexamer emission. So if you want to bring two molecules very, very close to each other, you can do it. So again, here you take this picture. This is, for example, the pyrene in some organic solvents, at a concentration, like a micromolar or less, you see only fluorescence, only the fluorescence here. That is the emission that you see for this. On the other hand, in water, if you put it, now you see a very strong, not very strong, but you see X-hammer emission. Okay. So this is cyclodextrins, and this one is no cyclodextrins. Tell me why in the presence of cyclodextrins you see X-hammer for the same concentration. We didn't change the concentration. We have the same solution in water, and you see this, and then add a little bit of cyclodextrin, you see this. So what does it, why does it happen? Okay. Okay. Why? Okay, I'll tell you why. So the pyrene is not water soluble. Okay. So it is soluble only to a tiny amount. But once you put cyclodextrin, this big barrel, there is a hole in the middle. So the pyrene will go in. But after the one pyrene goes in, there is still some space left inside the pyrene. So now the second pyrene will also go to the same place. Now if you notice here, see there are two pyrene molecules inside the cyclodextrins. So the concentration of this small area is very high. So now there are two, if you remember, for X-hammer formation, you need two pyrenes next to each other. So basically there are two pyrenes next to each other. Now you can see the X-hammer fluorescence. Basically what happens is, when it is in a solvent, it is completely surrounded by solvent molecules. Whereas when it is in a solvent, in presence of cyclodextrins, the pyrene goes inside. Since if it is a bigger barrel, then two of them can go. That means two molecules are sitting right next to each other. As soon as you excite, you see mostly X-hammer. Okay. So you can see, you can do the same thing. For example, this is the anthracene monomer, and then this is the anthracene in zeolites. You can see X-hammer. Okay. So here the zeolites are known, as I mentioned to you at the very beginning, it known to absorb water, lot of water it will take. So if you have the anthracene inside the zeolite and expose it to water, immediately what happens is you get this emission that becomes fluorescence. If you have a dry zeolite, then you get this emission. So the emission is changing whether you have water or no water inside the zeolite. Okay. Since you don't know much about zeolite, I will tell you what happens here. So the zeolite interior contains a lot of cations. The zeolite is the one that you use dry solvents. When you want to dry the hexane or benzene or something, we put molecular sieves inside the solvent. Molecular sieves are basically zeolites. So what happens is, when there is a sodium plus, I mentioned it to you, there is a cation pi interactions. You remember at one of those things I showed you, weak interactions. If you have a cation, that means positively charged, it will always look for electron rich molecule. So inside the zeolite there is a sodium plus. So one pyrene molecule will go and sit on top of it. When it does sit, second one will come and sit on top of the same thing. So now you have two anthracenes, you get this. If you let a little bit of water inside the zeolite, the sodium plus will be complexed by water. Now there is no interaction between the sodium plus and water. This would be released. So basically you get back to fluorescence. So you can control this fluorescence monomer and X-hammer by controlling the water inside the zeolite. So this could, now if you really want to call this as a sensor for water. Okay, same thing here, we don't need this. Okay, yesterday I showed you polarity probes. Suppose you want to know some remote place which you cannot go in and find out whether there is inside there is a little bit of water or no. Or does it look like a benzene or looks like chloroform, you want to know. So for example, these are all tiny small areas. This is a molecule, a cage, and inside the cage you have no idea what it looks like. Okay, you want to know what it, because you would like to know how this interior of this cage looks like. If it is a bigger bottle, you can look at it and tell. If this is millions and billions of size smaller than this, nobody can tell. All you need to do is to send something very small and go inside and come back and tell me whether it looks like there is any water inside. Okay? We said you can use pyrene for this purpose. Remember this? I told you pyrene, you can use it as a polarity probe. No? Yesterday I told you, it is only one day between yesterday and today. Okay? Do you remember I said the intensity I1 by I3? Pyrene emission has got, looks like this. So if you look at the intensity of these peaks I1 and I3, if you know the number, you can tell how inside is water, or inside is hexane, or it has nothing, no solvent inside, in a tiny room. Okay? So these are very useful to know. For example, you do this. So when it is very polar, I1 by I3 is high. When it is non-polar, I1 by I3 is small. I1 is this height versus this height. When you take the emission spectrum, you measure the height of this to that, and then if you can tell whether inside has what kind of polarity it is. So this is, for example, in methanol, and then this is in hexane. Okay? So you can see how dramatically the emission keeps changing depending upon the polarity. So using this, now the polarity is the probe. The pyrene is a tiny one molecule of pyrene. You can send it in and then measure the emission and record the emission and then look at this number. You can tell, well, for example, if you take a zeolite, the inside is very polar, because the inside the zeolite, it contains a lot of water and then a lot of salt. And then if you go inside the micelle, for example, sodium dodecyl sulfate micelle, the polarity is actually less polar than water, because although it is in water, the micelle's interior is not in water. There are no water molecules inside the micelles. That's what it tells you. And then, so this sort of stuff, so you can use this the fluorescence molecules as a probe to track what happens inside these things. Okay? So there are lots of other molecules like this. Pyrene and some of these molecules, what happens in the emission spectrum will shift with respect to the solvent. So then you send the molecule inside and then record the spectrum and you can tell what is the. Okay? Now the last few slides. Okay. Have you heard of this compound? No? Okay. This is called cyclobutadiene. Cyclobutadiene is a very famous compound. Okay, you think the benzene, right? This is a benzene. It is very stable. This compound. This compound is stable. And then you take this compound, right? And then you take this compound. Okay? Compound number 1, compound number 2, compound number 3. Okay? Tell me which of these 3 compounds, which one is the most stable compound? Which one? Okay. So one is benzene, that is, she thinks is the most stable. Number 2 is cyclobutadiene, that is this compound. And then third one is cyclooctatetraene, that is the third compound. Okay. Of these 3, which one is the least stable compound? Number 3. Okay, she thinks number 2. You want to change your mind or no?
No.
2.
I think it's number 3.
Number 3. Okay. Number 1 is the most stable. Number 2 is the least stable compound. I don't know, you must have studied this again. There is some rule called as 4n plus 2. Right? 4n, 4 electrons, 6 electrons, 8 electrons, like that. So this is called Huckel's rule. 4n plus 2, when you have n is equal to 0, 1, 2, 3. 4, if it is n is equal to 0, that is 2. N is equal to 1, that means 6. And then, so this one has got 6 electrons. So this is 4n plus 2. And then this has got only 4 electrons. And then this one has got 8 electrons. So this compound is aromatic. These two compounds are not aromatic. And this one is bigger. But this compound is planar. So it is 4n. 4 electrons in the cyclic structure is the most unstable compound. That is called anti-aromatic. You must have studied this rule, Huckel's rule. Okay, this is on the organic chemistry you study this stuff. So this compound is well known not to be stable. You cannot even make the compound. So because what happens is, as soon as you make it, it will react with itself, and then you go to this. Okay. So the thing is, people have worked on this compound for 20, 30 years, trying to make a compound. So it was, whenever you make it, it will disappear. As soon as you make it, it's gone. Because one molecule of this, another molecule of same one will react and then goes to give you cyclopentane. Suppose you want to make this compound. How do you make it very stable? Is somehow or other you have to keep the second compound away from the first one. The only way you can do it is, suppose as you make it in a small container and it cannot meet another compound. If it doesn't meet another compound, then it is stable. Okay, so this was the famous paper. This is the compound. So if you take this and put it inside a container and then irradiate this, it will produce cyclopentadiene. Once it produces cyclopentadiene, inside, if you produce a cyclopentadiene inside the capsule, it is not going to meet another one. Now it can be very stable. And that was published by Cram in 1991. So that tells you the power of the supramolecular structure. So if you make a compound inside another compound, that chemistry can change completely. Okay? This was done by the name Cram. Cram is the guy who got the Nobel Prize. So there are a lot of compounds like that. You take this, put it inside a capsule, and irradiate, you get cyclopentadiene. You take this compound, this is called benzene. Again, in organic chemistry, you might have studied benzene. Benzene is very reactive compound. It is not very stable. But as long as you keep it inside, it can be stable. Because these benzenes react with oxygen, they react with anything that you themselves. So, but if you protect it from everything, it is going to be very stable. Same sort of stuff. Okay? I think maybe that will be 3 minutes or more here. Okay, so you can make it with various types of carbenes and cations, and all these things are known to be unstable. You can make them very stable. So the chemistry, when you do it in a very small place, is different from doing it in a big beaker. Okay, so hopefully that's what I tried to tell you today, and we will see you tomorrow. Now is the lunch time. Okay? All right. Good.